It's time for OSPF to take a huge step in the world of efficiency as we look at our special area types and options that we have at our disposal. First thing that we'll talk about as we get into some of these special options of OSPF is the place of virtual links. You'll find out very quickly virtual links do not belong in your network, but may be there if you have a potentially band-aidable situation. We'll see that in just a moment. We'll then look at the special OSPF area types, which is one of my favorite topics just because of the names of these area types and what they can do for you in terms of efficiency. The whole time going through this, I plan on doing live demonstrations of these areas so that we can see the implementation and verification to make sure that these areas are doing what they say they should. Well, let's start things off by breaking the rules. That's what OSPF Virtual Links is all about. Now, looking at the network diagram that you see on the screen, you should have one word in mind, and that is impossible. You can't do that. You can't have multiple areas daisy chained away from area 0 because it violates the OSPF design boundaries, which are every single area has to be directly linked to area 0. Well, this is an exception to the rule, and that is what virtual links are all about. First thing I'll say about virtual links is that they are a poor design criteria. You would never design a network like this with virtual links in mind. What virtual links are there for are sort of a band-aid process, kind of just a way to make things work until you can redesign the network. For example, maybe area 0 represented, the 100 routers that you had at the corporate offices in California. Area 1 represented, about 20 different branch offices you had located in Australia. Well, Australia got aggressive and took over the competing Australia company, and with a hostile takeover, merged maybe the Nabisco headquarters in Australia with the Hasbro headquarters in Australia. Now, I don't even know what those two companies have in common, but they acquired each other. And so for the time being, you have the need to link in the Hasbro networks directly into the offices in Australia, and they don't have a direct connection back to Area 0. That's a place where the virtual link can come into play. Now, as of right now, I have a configuration set up to where router 4 is completely immersed in area 0, and it's already configured. Router 3 has one interface in area 0 and one in area 1, making it an area border router, and it is already configured. Router 2 is yet unconfigured because I want to show you what exactly happens when we set this up. So I'm going to start off on router 2. Do a show IP protocols, verify there are no routing protocols running. I'll do a quick show IP interface brief, and you can see that I have my link over from router 2. I've got a WAN link to router 3 up here, and that is this guy, 10.1.23.1. I also have a LAN link in area 2, that is 10.1.1.1 over here, that we're going to get up and running. So let's set this up. I'm going to go into router OSPF1. First thing I'll do is set my router ID to 2.2.2.2. And by the way, we'll find router IDs are of the essence at this point. You'll see that in just a moment. I'm going to type in the network, and we'll focus on the WAN link first. 10.1.23.1, 0.0.0 is going to be in area 1. That is the WAN link going from router 2 up to router 3, and sure enough we see the neighbor relationship form, and I want you to see that as of right now everything is fine. There's no error messages happening because that is a valid design. Just having router 2 sitting in area 1 has not broken any design constraints. Now I'm going to add in the LAN interface. I'm going to say network 10.1.1.1. Nope. All zeros, and we'll put that in area 2, which makes router 2 an area border router and now violates all of the OSPF design rules that we have put in place because area 2 is not directly connected to area 0. Now, what's going to happen as that gets added to the process is router, let's see, we are on router 2 right now. Router 3 is going to start barking. And you can see the end of some little message coming through right there. But I'm going to just give it some time, pause the recording right here, sitting on router 3 for the error messages to start coming through. Well, after waiting 38.3 hours, the error message never came. With some of the newer iOS versions, it actually will report an error whenever a virtual link is needed, meaning it'll come in and say, hey, router 2 is reporting that it's got area 2, and that's not allowed here. So it helps you troubleshoot. In this case, we don't see any error messages, but we're not going to get that route. Router 2, if we jump back over here, had the 10.1.1.1 network over here on Ethernet 0, and that route is not showing up at router 3. I'll do a show IP route. You can see nothing there, and it's definitely not showing up over at router 4, which is receiving the inter-area route. It's receiving the WAN link between router 3 and router 2. However, it's not receiving this 10.1 network back here, this Ethernet network. So what we need to do is configure a virtual link between router 3 and router 2. Here's the syntax to do it. First thing is you need to know that this is dependent on the router ID, the name of the router. This is that one criteria I was telling you, that if the router ID suddenly changes, this virtual link will break. It will no longer function correctly. The way you set it up is you go on router 3. I'll start off with router 3, the one that is linking it into the backbone. And go into the router OSPF process. And you type in the command virtual link, or sorry, not virtual link. You type in area followed by the area number. And in this case, we are looking at area 1. Area 1 is acting as the virtual link area, followed by the command virtual link. You can see area 1 virtual link question mark, and it's saying, what is the IP address or the ID? That's the one to keep in mind. Associated with the virtual link neighbor. This is the router ID. So I'm going to say router 2's ID is 2.2.2.2. Enter. That builds the bridge over to router 2 to say you now have a virtual link. Now, I want to mention that router 3 and router 2 are directly connected over that WAN link. But the command would be the same even if there was 20 different routers in between them. There could be, you know, a router 3 linked up to router 9 right here that's linked to router 10, that's linked to blah, blah, you know, this link goes on and on and on. And eventually it links to router 2. But the point is, I would type in the same command. The virtual link is formed with that neighbor. We're looking for the other ABR that is linking us to the discontiguous area, if you will. Now, we're not done yet because I have to go over to router 2 on this side and form the virtual link the other way. The command is going to be the same, meaning I'm going to go into the router process and type in area 1 virtual link, but now I'm going to type in the router ID of router 3. So I'm going to jump back over to router 2 here, get into global configuration mode, followed by router OSPF 1. And I'll type in area 1, again, the area that the virtual link belongs to, space virtual link, and then I'm just going to type in the router ID of the neighbor, 3.3.3.3. What will happen when I hit enter on that command is a virtual link is formed between those two neighbors. Now, a virtual link is a tunnel. I don't know if you've had experience with tunnel interfaces, but it is a tunnel that makes router 2 believe it is directly connected to area 0. As a matter of fact, in the CCIE lab, one of the things that you may be asked to do is to form virtual links without using the virtual link command, meaning you have to resort to using tunnel interfaces because they do exactly the same thing. The tunnel interface tunnels the packets through so that router 2 in this case believes it is plugged right into area 0. Now look at this. It says the process OSPF VL0 is gone from loading to full, and the loading is done. Type in show IP OSPF neighbor. You can see that the neighbors look the same. We have that same neighbor with router 3, but when I type in show IP OSPF virtual link, it shows this new point-to-point virtual link that is a tunnel interface. Now, the tunnel interface doesn't actually show up in the show IP interface brief or anything like that. It's just shown right here, and this is your way of being able to check the status. Just type in this command and verify that the link is up. The only reason it would fail is if we typed in a bad router ID or the router ID somehow changed between those two neighbors. Let's check the process over on router 3. That virtual link should be up. I'm going to type in a show IP route, and sure enough, look at that. It has an inter-area network, 10.1.1.0/24, that it now has picked up from router 2. That's its Ethernet 0 interface over here in area 2 that it wasn't picking up before because that was seen as a discontiguous network. Now we should also see that over on router 4. Do a show IP route over here. And sure enough, there it is. The route shows up as 10.1.1.0/24. It has now appeared coming from that one neighbor. So that tunnel interface is successful, and router 2 is able to advertise its discontiguous routes over across the network. Now you can do virtual links within virtual links. I'm not going to show it to you because it's really ugly, but what you could do is, let's say you had, another hostile takeover that took place and ended up with area 3 over here with a router connected like that. You can virtual link these routers together and then virtual link router 2 and router 3 together. It gets very ugly and very confusing, but it is possible, and it'll allow those routes to traverse over. Again, this is not a way that you would purposely design a network, but rather a band-aid that helps it work until you can redesign it to link all the areas directly. Now, before we get into the next topic, I want to do a little review on the OSPF areas, as in their purpose. Remember, we divide the network into areas when the SPF algorithm has begun to run too often. Updates have become too numerous because the network has grown too large. So by splitting into multiple areas, we make that topology database smaller for the routers within those areas, so they have to run the algorithm less often. The reason that is because we can do summarization at this point. We can summarize at the area boundaries. As soon as we do summarization, we get those new LSA types that we talked about in the previous video. The LSAs are the building blocks of OSPF. They advertise routes. They advertise routers connected to the same switch or the same subnet. That's the LSA type 2. The LSA type 3 and 4, the summary LSAs that get generated anytime we have an ABR that passes routes from one area to the other. Those are always marked as LSA type 3. LSA type 4 identifies the ASBR, its IP address, its location. And then the type 5 LSA was the LSA that the ASBR generated anytime it sent external routes into the OSPF domain. I wanted to do that review because the function of these special area types that are coming up help you to manage and filter these LSAs. Let's take a look. Behind the scenes, I went ahead and built the network that you see here on the screen right now. 3 different areas, 5 different routers. Router 3 being the ASBR, bringing RIP routes, redistributing them into the OSPF domain. And we broke it up into multiple areas because, the routes were getting a little crazy. We want to manage our routing tables. But let's take a look at router 1. I'm going to jump over to router 1 on the terminal and do a show IP route. And you can see that router 1 is getting all of the inter-area routes. You can see the WAN links that are coming from other areas. We've got the external routes that are being shot in from that RIP router. You can see them as the E2 routes. So even though I've implemented multiple areas, router 1's still getting all of these different routes. And the irony of this all is that router 1's only way out of area 2 is router 2 in the first place. So why on earth would I want to fill router 1's routing table with all of this routing information and all this detail about the WAN links in the other areas, the RIP external routes, when router 1 doesn't care? I mean, router 1 just knows to go to router 2 to get out in the first place. It's almost as if router 1 is better fit for just a static default route than it is to run the full OSPF. But, at the same time, we are running OSPF, and one of our administrative challenges has been to remove all the static routing. So we want to run OSPF, but, do you see our dilemma? Well, that's where this concept of stub and totally stubby areas come in. I love this concept for the sheer fact that I love saying those names. I'm convinced that whoever created these had to come from California, because they were probably thinking of Yeah, let's create an area and let's call it a stub. And a stub will have the criteria that it will block the type 5 LSAs from entering that area. But, you know, we want to step it up even more. Do you feel the California coming in here? And maybe we want a different kind of area that's like totally stubby, man. And that totally stubby area is going to block all the LSAs from other areas like type 3, type 4, and type 5. Those will all be blocked from entering these areas. That's my envisioning of how this process was created. So that's the two different kind of areas. Is a stub area, or what's called a stubby area, will block type 5 LSAs from entering. Now think back, we did the flyby review. What was the type 5 LSA? It was the external routes. Any route that was sent in from router 3 will be blocked from entering a stubby area. These are a piece of cake to configure. I'm going to go into my router, and let's start off, let's see, on router 2 over here, the ABR. And I'm just going to type in the OSPF process, area, and this is area 2. Area 2 is a stub. That's it. As soon as I do that, area 2 is now configured as a stub, and the neighbor fails. Because if you remember back to the hello packet, one of the things that must agree in my neighbor relationships is the stub flag. It was one that was way down in the list, and I said, oh, we'll talk about the stub later. This is where we talk about it. The stub flag has to agree between neighbors, so that means I have to go back to router 1, go into router OSPF process, which has to be done from global config mode, get into the router OSPF, and I'm going to type in area 2 stub, same command. Now, as soon as I do that, we're going to see the neighbor relationship reform between router 2 and router 1, these two routers right here. Now, router 1, I don't think reports the neighbor relationship up and down to the screen. It's the logging method I have turned off. I'm going to type in show IP OSPF neighbors, and sure enough, it has reformed that neighbor relationship. But let's check out what's different. I'm going to start over on router 2 and do a show IP route. Router 2 is the router that is connected right here to the backbone and area 2. Now, router 2 shows no change in the routing table. It's still seeing those external routes, the routes that the stub area was supposed to stop. Oop, my slide got jumped there. The stub area was supposed to stop, but that's okay because router 2 is the ABR. It has all the info from area 0 and all the other areas that are being injected, and all the info from area 2. The point of a stub area is it's supposed to filter the information from reaching the routers in the area, not the ABR. The ABR is always going to have all the info. So let's jump over to router 1 and see if that's really taking place. I'm going to type in show IP route, and sure enough, you can see it in action. All of the external routes have disappeared from router 1's routing table and been replaced by this route right here. A default route is automatically generated by the ABR that says, hey, I know I'm filtering the routes, but you can send anything that you don't know about to me because I know all of those routes still, and I will be able to get you there. We've effectively shrunk router 1's routing table from something that looks like, let's scroll up here, right there, that was its old routing table. Something that looks like this with all the external routes, all the way down to this that just has the default route here in play. Now, I know it doesn't look like much, of course, in a lab environment because there was only 3 external routes coming in. But man, they can have a huge impact if you have a ton of external routes that are being redistributed into the domain. Well, let's take a look now at the totally stubby area over here in area 1. Remember, these types of areas should block everything from coming in. So I'm going to bring up my prompt and hop over to router 5. That's the router way over on the right-hand side. Just to verify right now, show IP route, that it's getting all of those routes. Yeah, you can see external routes are flooding the table. Other areas are coming in, flooding the table. We've got a huge routing table here, relatively speaking. So I'm going to change this area into a totally stubby area. Now, the first thing I want to mention is TSAs, or totally stubby areas, are Cisco proprietary. This is not an industry standard thing, although many other vendors have implemented it in their own ways. This is something that is supported only on Cisco routers. So I'm going to jump over to the ABR first, router 4, and go into the router process to turn this feature on. Now, even though this is a Cisco proprietary feature, the only one that has to be a true Cisco device is the ABR. Router 4 is going to be doing the filtering. Stub areas, the stubby area feature, is an industry standard. So as long as Router 4 is an industry standard capable router and can run the stub area flag, then it can handle the totally stubby area just fine, because Router 4 is the one really the one doing all the filtering. Did I say Router 4? I meant Router 5. Router 5 is the one that's just receiving what Router 4 has to say. Here's the command to type in. It's just one more step. Area, what area was that? Area 1 will be a stub, and we take it one step further and type in no summary. Stub, no summary, enter, converts that into a totally stubby area. Now you can see router 5 immediately fails because the stub flag doesn't agree anymore. You can see the neighbor relationship has been reset. So I'm going to come over to router 5, and just to prove it to you, I'm going to go into OSPF and just type in area 1 stub. I'm not going to turn on the no summary flag. We're going to keep this one industry standard and not use the Cisco proprietary feature. That should bring the router relationship back online. There's my router. It's back online. I'm going to type in show IP route on router 5. Now, what should we expect to see before I hit that enter key? Router 4 is a totally stub area blocking type 3, 4, and 5 LSAs. That is any external route, that's type 5, any ASBR IP address, that's type 4, and any intra-area routes, that's type 3. Those are supposed to be the summaries from other areas. So I should see just a default route. And sure enough, we do. You see, router 5 has received nothing but a default route from router 4. Everything else has been removed from its routing table. Now, if this was a real area, it would probably have more routers in it, and we'd see other routes coming from our own area. But router 4 effectively filters everything from router 5's routing table and its topology database. So router 5 should have a completely clean database. I'll do a show IP OSPF database, which has very little information, just saying, hey, this is the router that's advertising your one summary route, which is our route right there. But everything else has been minimized down to nothing. Talk about saving some processor cycles. That's what the stub and totally stubby areas do. Now, if the stub and totally stubby areas did not convince you that some beach surfer in California created this concept, this one definitely will. It is, no joke, a not so stubby area. Again, I can see the conversation because here's what happens on the screen. You can see that area 5 used to be a totally stubby area. And the guy was like, oh yeah, the totally stubby area stops all LSAs. It's good. And then all of a sudden, some design flaw jumps in the midst of thing, and router 5 gets connected to an external RIP network. And the California guy goes, oh, no way. Oh, then I guess this is like a not so stubby area. Well, but it's totally stubby, so maybe it's a not so stubby, totally stubby area, dude. Yeah, that is, I kid you not, the technical term for what area 1 would be. Take a look. I've got router 5 sitting in area 1. I'll do a show IP route. You can see it's still configured as a totally stubby area. I've got to get out of that voice. But it's because it's still getting the default route. All of the OSPF routes have been filtered. But the problem is router 5 ended up connected to a RIP network out here. So now you have router 5 in area 1 that's essentially an ASBR. right? Because it's needing to send these RIP routes to the rest of the OSPF domain. But in itself, it violates the whole rule of a totally stubby area anyway. Do you see what I mean? I mean, how can you have an ASBR sitting in Area 1 when Area 1 is still a totally stubby area, just like it was before? Well, that's where the not so stubby area comes in. What it does is it passes external routes through a Type 7 LSA. This LSA was engineered to kind of trick the Area 1. Even though Area 1 is still a totally stubby area and it denies Type 3, 4, and 5 LSAs, the people that B created this area and said, well, if it's denying those 3 LSA types, and we need type 4 and 5 to really have an ASBR sitting in area 1, let's just go ahead and trick it. Let's make up some other LSA type. Let's make it type 7. And type 7 LSAs will tunnel through this area. So as router 5 sends those RIP routes over to router 4, they come across this type 7, which all the routers in that area, if there were other routers, would just say, that's a different LSA. We're not filtering that, even though we're totally stubby area. Router 4 gets it and immediately realizes, aha, type 7 LSAs, those are external. So as I send them into the rest of the network, I will send them as type 5 LSAs. It converts them back to the original form that they were, or the original form that they should be, to be considered external routes. So type 7, just like we saw virtual links kind of tunneled areas through each other, these LSA types sort of tunnel through stub and totally stubby areas. And that's, by the way, where the names come from. A not so stubby area represents a stub. A not so stubby, totally stubby area represents a totally stubby area. So here's what the config looks like. I'm going to go on router 5 and go into router OSPF 1. And the first thing I'm going to type is, this is area 1. I'm going to type in area 1 stub and then put a no at the front of that. I'm turning off the stub capabilities because I need to convert this into a not so stubby area. The way I do it is type in area 1. Instead of a stub, I'm going to type in NSSA. That stands for not so stubby area. Just so you know, I didn't make that word up. Now I have to go over to router 4. Okay, router 4 is the one, and I don't know where I'm at here. Router 4 is the one that originally converted this into a totally stubby area. I'm going to type in no area 1 stub, no summary, which is the totally stubby flag. And I'm going to type in area 1 NSSA, not so stubby area, plus no summary. That's how we put the, I need to just type in no area 1 stub to turn off the stub flag. There we go. Area 1 NSSA no summary, which now says this is a not so stubby, totally stubby area, and it will still be filtering those routes out. Before we do the redistribution, let's go over to router 5, and sure enough, we should be able to see router 5 is, there we go. Just took a second. Router 5 is now receiving that default route from router 4, just like it was configured as a totally stubby area. But now router 5 will be able to redistribute those RIP routes to router 4, and router 4 will receive them as those type 7 LSAs. Let's do that. I'm going to go into router OSPF 1, and again, I know we haven't talked about redistribution yet, but I'm going to type in the command redistribute RIP, which sends all RIP routes into OSPF. And I need to set a flag of subnets, and I'm going to set the default metric of these routes to just, let's put them at 10. And I'll explain that whole command later on. That sends the RIP routes into OSPF. Now, actually, before I do that, I'm going to type in show IP OSPF database. And you can see, look at this, we have type 7 external link states, routes that are being received via RIP. Now, I have some routes in here that shouldn't be there, but that's just because I'm kind of simulating the RIP network behind us. These are the routes that are coming in via RIP. Okay, you can see all of them in the routing table, RIP routes. jumping in here, that are being advertised in the database as type 7 LSAs. Now let's hop on over to router 4, do a show IP OSPF database. And you can see they're being received by router 4. Look at this. Router 4 is receiving them as type 7 LSAs as well, but it is advertising them out as type 5 LSAs. Now, the list shrinks down here. You can see I have a bunch of type 7s, and then it shrinks down to just one of them. The reason it shrinks down is because, as I mentioned, some of these should not be showing up in the RIP routes. They just are because I'm simulating them. So it's correctly adjusting them as it's advertising them out as type 5. Now, if I were to come up here to, let's jump over to router 2. Router 2 should not see type 7 LSAs at all. It should only see the type 5 because router 4 is doing the conversion back to type 5. Type 7 is only between routers in that not so stubby area. So I'm going to type in show IP OSPF database, and just as expected, type 5 LSAs are the only thing that we receive. You see some summaries. Those are the type 3s and 4s. The router, that's type 2. Some other summaries over here. Some other router link states. Those are type 2, type 1. But overall, we can see that there are no type 7 LSAs. They've all been successfully converted back to the type 5. Last thing I'll say on not so stubby areas is that they're usually design goof ups. They're usually set up where you had the stub or totally stub, and then, oh, we had some external network that we merged into, or whatever the case may be, and we have to redistribute. So in the interim, while we're redesigning the network, we'll convert it to a not so stubby area to let things work in the meantime. Last thing I'll mention in general with the stub and totally stubby areas is that you've now seen a major method you can use to reduce the routing tables and topology database in huge ways on the routers in these fringe areas. With those design options comes one major criteria, and that is there should only be one exit point from a stub or totally stubby area. You can have multiples for redundancy, but if you do have multiples, keep in mind that you have now dual default routes that are going to be injected into a specific area, making the routing potentially inefficient if you design it poorly, meaning that you end up having load balancing happening when load balancing shouldn't be happening because router 1 doesn't really have an idea of what is beyond its own area, depending on the type of stub you deploy. So that's why they call them stub and totally stub, is because those areas are supposed to be just a stub of the network. There's only one way in and one way out of them. And on that note, let's wind things down. We started off this whole video by taking a look at virtual links, which is essentially a band-aid for the network, a way to patch the network while you redesign it so all areas are directly connected to area 0. We then got into the special OSPF area types, which are the stub, the totally stub, and the not so stubby area, and saw the implementation of those one by one as we walked through a live topology and saw the effects of each one of those area types on our routing tables. I hope this has been informative for you, and I'd like to thank you for viewing.